Welcome everyone, and welcome to Bird Math. Thanks for watching. Today, we're going to be talking about finding areas under curves. And this is going to be part one of a two-part series devoted to the topic. In part one, we're going to be showing you how to estimate areas under curves, and in part two, we're going to be talking about how to find exact areas under curves and how it relates to the calculus topic of integration, in particular, definite integrals. So let's get started. Here you see a nice second-degree polynomial, f of x equals 1/4 x squared, and we're focused on the interval from x equals 0 to x equals 6. And we want to find the area under the curve of f of x from x equals 0 to x equals 6. And that means the area between the function and the x-axis. And you'll see this area, this region, is shaded in blue here. And so we want to find the area of this shaded blue region. Now, up until this point in your calculus career, finding areas is a relatively simple thing to do. You've been dealing with nice shapes like squares and rectangles and circles and trapezoids and triangles, etc. And so you've had a nice formula to use when you want to find the area of a particular region or shape. Unfortunately, in this case, this blue shaded region doesn't fall under any of those categories, and we don't have a general formula to use to find this area. So we're going to have to be a little bit more clever here. So, how can we go about this? Well, one thing we can do is try to estimate it. We can at least estimate this area. And how are we going to estimate the area under the curve of this function f of x? Okay, so you'll notice here this is the exact same function, just drawn by hand. F of x equals 1/4 x squared. And we're interested in finding the area under the curve of this function from x equals 0 to x equals 6. So to estimate it, what we're going to do is basically split up the area, the shaded region, into rectangles. Now, doing this requires the use of a few different variables, and it's a little complicated to keep track of. So I'm going to walk through it slowly. Hopefully, you can follow along. So the area under the curve from x equals 0 to x equals 6, we'll call the starting point A and the ending point B. So for f of x, the area under the curve from A to B. And what we're going to do is we're going to partition or split up this interval 0 to 6 or A to B into n equal subintervals. And in this case, I picked n equals 6. So n is going to be the number of subintervals or rectangles to use. So when I do that, I split up the interval 0 to 6 into 6 equal subintervals or rectangles. Each one of these subintervals has the exact same width. So this subinterval from x equals 0 to x equals 1 has the same width as this subinterval, x equals 1 to x equals 2, and so on. And we can look at these subintervals like they're rectangles. Now, that's the width of each one of these rectangles. What's the height of each one of these rectangles? The heights of each one of these rectangles are not equal. They are all different, and they depend on the value of the function. In this case, I decided to use right-hand side endpoints. So, for instance, for this subinterval from x equals 1 to x equals 2, you take the right-hand side, x equals 2, you draw a line from the x-axis to the function. That's going to be the height of this rectangle. For this rectangle, from x equals 0 to x equals 1, you pick the right-hand side, so in this case 1, draw a line till you hit the function. That's going to be the height of rectangle 1, and so on. And you'll see we have 6 rectangles of equal width. but varying height. Now the width of each one of these rectangles, or subintervals, is typically denoted by delta x. And the formula to find the value of delta x is b minus a over n. So b was the endpoint of the main interval, so in this case 6. A is the starting, so in this case 0, over the number of subintervals, so in this case 6, equals 1. And that makes sense. Each one of these rectangles has a width, or delta x, of 1. So why did I do this? Why did I split it up into rectangles? Well, it turns out that finding areas of rectangles is very easy. The area of a rectangle is simply length times width. So if we wanted to find the area of, say, rectangle 3, what we would do is look, well, the length or height of rectangle 3, because we used right-hand endpoints, is simply f of 3, and the width, as it is for every other rectangle, is delta x, or in this case it'd be 1. And hopefully you can see now that if I added up the area, I summed the area of each one of these rectangles, 1 through 6, I would get a total area, not exactly, but somewhere approaching the true value of the area under the curve. Certainly, because we used right-hand endpoints and the function is increasing from 0 to 6, it's going to be an overestimate. You could see this green shaded region of each one of these rectangles is over the function. So it's not going to be exact, but it's a starting point. It's something. So let's do that. Let's calculate the area of each one of these rectangles. Okay, so we're going to sum the areas of each one of these rectangles together, and we're going to claim that the area, which I call big A here, is the area under the curve of the function from 0 to 6, is approximately equal to the sum of each of the areas of each one of these rectangles. Area rectangle 1, rectangle 2, etc., all the way to rectangle 6. Now, we want to, whatever we do in math, we want to kind of generalize it to where it could be used later on. So instead of putting in the actual values here, like, for instance, the subinterval from 0 to 1, I can write each one of these endpoints of the subinterval, x sub 0, x sub 1, x sub 2, etc. So, for instance, if I want to find the area of rectangle 1, I'm going to multiply the width of the rectangle, which we already found is delta x, and the height of this rectangle is the value of the function at the right-hand endpoint. So in this case, it would be f of x sub 1. If I want to find the area of rectangle 2, well, the height is delta x, and the width is delta x, and the height of this rectangle is the value of the function at x sub 2. So because this is very tedious math to write this all out, and this is only 6 rectangles, imagine if we had 20 rectangles or 50 rectangles. And you'll see more of that in part 2. I think it would be a much better way to go about this would be to use sigma notation or summation notation. And if you don't know how to do that, check my channel. I'll have a video explaining how to use sigma notation, but I'm going to assume you know how to use sigma notation. And I can rewrite this big, long, unwieldy sum as the following. I can say that the area under the curve is approximately equal to the summation from I equals 1 to n f of x sub I times delta x. And x sub I for right-hand endpoints, a formula to get each right-hand endpoint of the subinterval is a plus delta xi. So I know this might be a little overwhelming, but let's just go through it nice and slowly. So let's find x of a sub I first. Well, this says it's a plus delta xi. Well, remember, the main interval we're concerned about as far as area under the curve is 0 to 6. So a is the starting point, 0, plus delta x we found is 1, that's the width of each subinterval or rectangle, times I. And so this becomes 0 plus 1 times I, or just I. So we can plug that in here. We could also plug in n, because if you remember, n is 6. It's just the number of subintervals or rectangles. And we plug that into the function f. Well, f is 1/4 x squared. So this becomes 1/4 I squared, because that's what x of I is here. And then times delta x, which we know is just 1. Let's just simplify this. A property of sigma notation is you can pull constants like 1/4 and 1, which is just 1/4, out in front of the sigma sign. Okay, and another formula related to sigma notation that you should know, I'm going to assume that you know, is the following. The summation from I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 over 6. It's just a good general formula to know when you're dealing with these problems. And so hopefully you can see we can use that here. So this becomes 1/4, and the sigma goes away now when we use this formula, because n is 6. This is just 1/4 times 6 times 6 plus 1 times 2 times 6 plus 1, all over 6. Area is approximately equal to 1/4 times, what's 6 times 6 plus 7. I'm sorry, 6 plus 1 is 7 times 6 times 2 is 12 plus 1, 13, all over 6. And when you do the math, this works out to be 91. And then that 1/4 times 1/4, 91 over 4. And so this is our first estimate of the area under the curve of f of x equals 1/4 x squared. And just as a recap, we couldn't find the value, the actual area exactly, so we decided to estimate by partitioning the interval from 0 to 6 into 6 equal subintervals of with delta x, in this case 1, and we used right-hand endpoints, which means that when we use this formula, the summation from I equals 1 to n, f of x of I delta x, our delta x is a plus delta xi, which in this case, because delta x is 1, a is 0, just works out to be I. You plug in I to the function, f of x, you get this. You simplify down until you get here, and you use this summation formula for I equals 1 to n, I squared. So we know that 91 over 4 is an overestimate, but it's our first estimate. And in part 2 of this video, we're going to show you how, with the principles of calculus, how, and this is, by the way, going to be leading into what's known as a Riemann sum, of how the more rectangles that you use, in this case we use 6, but what if we use 12 rectangles? What if we use 30 rectangles, or 60 rectangles, or 100 rectangles? You'll notice that as n, the number of rectangles or subintervals, increases, the estimate gets more and more accurate. And that should set off alarm bells in your head to remind you of the limiting process in calculus. And we're going to go over all that. So we're going to end it here. Thanks for watching. Thanks for watching Bird Math. Look out for part 2, and I hope to see you again. Bye.